Okay, so last Tuesday we have stated a couple of theorems about the zero sets of an analytic function. So now we will see an important application. It's about to identify the equality of two analytic functions. Okay, so let f of z and g of z be analytic functions. Okay, defined on a domain. So it's very important that we consider two analytic functions on a domain. And as we know, a domain is just an open connected set in the complex plane. Okay, now if the set of all points such that f of z and g of z has the same value, okay? If this set has a limit point in D, okay? So in the defining domain, then these two functions are identical on D. All right, so let's consider h of z to be the difference of f z and g of z, okay, which is analytic on D. All right. Now the zero set of h of z is just equal to the set here of points such that f of z is equal to g of z. Okay. I used big Z. Okay. And which has a limit point in the domain D. Okay. All right, so by theorem 16.2.c, H is identical to 0 on D. Okay. So this analytic function H should be identical to 0. So that of course F is identical to G on D. Okay. Okay, and right. So the current theorem can be used to establish, okay, identity among entire functions from their real counterpart. Right, and this we call phenomenon. Right, is historically called the principle of persistence. Of functional relationship. Okay. Right, so for example, to establish the identity, that's sine square of z plus cosine square of z equal 1 for all z in the complex plane. We know that its real part is real counterparts. Okay. It's sine square x plus cosine square x in 1 for x in R. Okay. Thus, we have the set that R, the real line, is contained in okay, and this is 1. Okay. And so and then we got the left-hand side is the analytic function of z, and the right-hand side is the other analytic function of z there. Okay. So this set contained the real line. And as we know that all right, so every point, we know every point, okay, in the real line, okay, is a limit point of R, of the real line itself. Okay, because right, so this is the complex plane, and if you take a point here, okay, so this is its x here. Now, for every neighborhood of this point on the real line, okay, you can see that it contains a point on the real line, okay, different from x. Okay, so you can find, say here, x prime. Okay, so you have x prime, and in the neighborhood. So every point on the real line is a limit point of the real line. Okay, every point of that. Okay, so of course that this said, so this implies that the set has a limit point in the complex plane. And as we know, the complex plane itself is a domain, which means that it is open and connected. Okay. All right, so this implies that the sine square z plus cosine square z equal to 1 for all z in C. Okay. Okay, so basically, if you have an identity about functions defined on the real line, then you can extend it to identity, okay, on a domain of the in the complex plane, okay. Right. So this is just applications for entire function. If you deal with function which is not entire, then you can consider functions, okay, in an open connected domain. So that you look at this set, okay. You look at the set and find that this set has a limit point in the defining domain. Okay. So this is very convenient. So because we learn a lot of identities, especially many identities in trigonometry, right? And they can be extended to the complex domain. Mm-hmm. Any questions? Okay. So I would like to state a theorem in the textbook about polar and zeros. Okay. So if a complex function f z is analytic at the point z equal to z0 and has a zero of mth order at z equal to z sub 0. Okay, so if f z is analytic at the point, which means that f of z is analytic in the neighborhood of this point, right? By definition. Okay, and this function is an analytic function. F of z has a zero of mth order at z equal to 0. Then the reciprocal of this function has a pole of mth order. Okay, and why it has a pole? You know, if it's a zero, right? So suppose this is the 0 of a function, right? So now, so we know there is a neighborhood. Every zeros of finite order is isolated, right? We have shown that, right? So they are isolated. So we can find that here, and so we have f of z is not 0, okay? In the punctured disk, right? Not 0, okay? And we know f of z of 0 is 0, okay? Since 0 of finite order is isolated, okay? And this has been stated in by theorem 16.2.3. Okay, so it is isolated. And so we can find a neighborhood of z0. Okay? So in this neighborhood, fz of course is analytic. And f of z is non-zero except the center z0. Okay, so that the function is with them. Okay, and so the reciprocal of the function f is well defined in the punctured open disk. Okay? And so that, but it is, but you can see that it's singular, right? At z equals z0. Okay, it is singular because that when z is equal to z0, the denominator is 0, so it's a singularity. Okay, it's singularity. Okay, right. And the theorem says that this singularity is actually a pole of m's order. Okay, so it's a pole of m's order. Right? So now, an analytic function, has a 0 at the point z0 here. Okay. Then it's reciprocal. Okay, has a pole. Okay, of m's order at z equal to z0. Okay. Right. So by taking the reciprocal of an analytic function, you turn a 0 of m's order to a pole of m's order. Okay. Okay. And so does right, so that of this ratio, provided that the numerator h of z, okay, is analytic at z equal to z0, and h of z sub 0 is not equal to 0. Okay, so this is the first statement. Now, and if a complex function f of z has a pole of m's order at z sub z0. And remember, when we define a pole of m's order, we mean that any pole is an isolated singularity, right? So that isolated singularity means that except this point, right, in the neighborhood of these singularities, right, no other point is singular. Okay, so every point is isolated, okay, because we define pole, right, from isolated singularity. Okay. So I have to say that a pole is an isolated singularity. Isolated singular point. Okay. Another type of isolated singular point will be isolated essential singular point. Okay. All right, so that if a complex function has a pole of m's order, okay, and so this is the case. You can look at that. All right. Now, if a complex function has a pole of m's order at z equal to z, at the point z sub 0, then the reciprocal f of z, okay, has this one is analytic. So it's analytic at z sub z0 and has a 0 of m's order at z sub 0, and thus so does the h of z divided by f of z, okay, provided that h of z is analytic at z equal to z0, and the value of h at the point z0 is non-zero. Okay. So this is about the exchanges of pole and zeros by taking reciprocal of functions. A very nice theorem in practice. Okay, so you know that. And the proof follow a standard procedure. So I will omit it. So please see the lecture notes. Okay. All right, so now I will take some time to discuss this Riemann sphere and the point at infinity. Suppose that we look at a three-dimension the space here. Okay. So this is our coordinate frame to here. Okay, and we place a unit ball. A unit ball is a ball with radius 1. Okay, so we put a unit ball sit on the xy plane. This is 0. Okay, so sit on the xy plane, and the south pole touched the origin. Okay, so you will have something like okay, so 0, 0, 1 is the center. So 0, 0, 1, the center of the unit ball. Okay. And the south pole here is the origin. Okay. Okay, so now this is the unit ball, and the sphere. The sphere is just the surface of the unit ball, so that is the set, right? Which coordinate satisfy this quadratic equation here, okay? Because the center is 0, 0, 1, okay? 0, 0, 1 is the center of the unit ball, okay, here. And so you can think about that the south pole just touched the origin, and then the north pole is the point 0, 0, 2, okay, 0, 2 here. Now you can draw a line, okay? So you can think about that. You have a light bulb here, and so every light, okay, they will go, right, and from here it will touch a point, okay, on the xy plane. So here you have an x and y and a 0 here. Okay? Right, so the light ray will go inside the ball, right? And then it will penetrate a point on the sphere. This is the point, okay? All right, and then the light, you can see the light here. And the light will touch the xy plane. Right? So that you can think about that the way here. Alright, and so this is the point here. Alright, or sometimes you can think about this is corresponding a z with, so as we demonstrate in section 14.1, I have demonstrates that we can build, we can identify topology or geometric property of the complex plane with the Euclidean plane, right? And we define the so-called neighborhood, open set, closed set, complex, a lot of things there. Okay, but so a point on the xy plane whose coordinate is xy0 and corresponding to a complex number which is z is equal to x plus iy. Okay, so that is the point. Okay, and we denote the north pole by n here. Okay, so n is just the 0, 0, 2 with this coordinate. Okay, okay, and now the north pole and the point here will intersect with the sphere, and this one is the P star. Okay, so we denote it as P star. This is P star. And what is this, the three-dimensional coordinate of this P star? Well, I can write it down. So the P star is here, 4x, x squared plus y squared plus 4, and for y, x squared plus y squared plus 4, and 2 of x squared plus y squared, to cloud it, sorry. Okay, so P star okay, and so the mapping from P to P star in the X in the sphere the mapping from P is called a stereographic projection. Stereographic projection denoted as pi. Okay, so pi cent goes to so you have the correspondence. Okay, and you can think about that. This is from X. Okay. And we know pi is 1-to-1, but not untrue, since pi of the plane is equal to the sphere, but without the North Pole. Okay? Without the North Pole here. Okay. The geometry of the complex plane, right, has the same geometry of the the sphere, okay, of the sphere X here, and but so that all right, so to make pi to be 1-to-1 and onto we extend the complex plane C to the extended complex plane we call C, and by adjoin C with an additional point we call infinity. C bar is equal to C union. And why we call it infinity is that we think about if we have as the projection, as the projection, okay, go over. So if the projection going to be parallel or as a tangent of the North Pole, then you can see that that points near the North Pole will project to points which is very far away from the origin. Okay, so as you can see that if so, okay, so maybe I will say if I have a plane to cut. So let's see. So if we have a plane to cut, we will have okay, and it will cut okay, a circle. Okay, so this is the plane z equal to 2 of 1 plus 4 divided by r square. Okay, and so we will see that the circle that okay, so we just say that z is greater than or equal to r, right? So if we consider a point on the compass plane which is far away from the origin, so that this is indicated by here. For big R, you see that the point on the compass plane, z, will be far away from the origin. And this said, if we do, okay, then its projection will be equal to on, or maybe I'll use greater than R, so it's equal to inside, so that it will be x intersect that x, y, z in R3 such that the z will be greater than or equal to 2 of the 1 plus 4 divided by r squared. Okay. So it will be cut by a plane. So this is the plane with a plane in R3. Okay. So the plane so it will cut through the point here. Okay, so here, so this point x2 divided by 1 plus 4 divided by r squared. Okay, so this plane is parallel with the xy plane. Okay, and cut through the point here. The z coordinate would be 2 divided by 1 plus 4 divided by r squared. Okay. Right, and so the projection to here comes to okay, and the radius is r. Okay, so a point will go over there, here. Okay, so this point is outside of the circle, the big circle. Okay, because z has distance from 0, from the origin, at least r here. Okay, so this is the point. Okay, and it will has a corresponding point which is just inside the circle, okay, cut by the plane here, so that you can see, of course, it's on the sphere, and cos s, okay, okay. And minus the North Pole. Okay, so we have to exclude the North Pole here. Okay, so you see that when the P star going to the P star approaching to the North Pole, okay, then the P will go the distance of P from the origin. Well, so this is the origin here. Well, goes to infinity. Okay, so we extend the convex plane by adjoining an additional point called infinity. Okay, so we think about that. We have just an additional point. You can imagine that point. Okay, and so that and assign the pi infinity to the North Pole. Okay. So in that way, pi, so now pi it goes to x1 to 1 and on to So now, so the stereographic projection, pi becomes 1 to 1 on 2. Okay, and now to make pi and its inverse, pi minus continuous all right, I just use B1 to 1 on 2. Sorry about that. So to make pi and its inverse continuous, so we consider z greater than r, okay, of the complex plane as the R neighborhood of the point at infinity. Okay, for all greater than 0. Right, and so this is corresponding to the neighborhood of the point and in the sphere x cut by the plane z by the plane z equal to 2 divided by 1 plus 4 divided by r square in R3. Okay, so in this way, the extended complex plane C bar and the sphere X have the same topological structure, or we can say geometrical structure. Okay, and in this sense, so the sphere X is called a Riemann sphere. So this is the idea that we think about, that we adjoint a point at infinity to the complex plane. Okay, so that we obtain a so-called extended complex plane, C bar. Okay, all right, and about the geometric structure, we need to know the neighborhood of the point at infinity. Okay, so we have from the stereographic projection, all right, because the point at infinity can be identified by the north pole of the sphere. Okay, and from the three-dimensional Euclidean space, we know that a neighborhood of the north pole, okay, or you can say it's just that can be described by using a plane, okay, parallel to the xy plane, and then to cut the ball, all right, and so that leave a piece of the sphere which is just in the vicinity of the north pole, all right, and we know this is actually a neighborhood of the north pole, okay, on the sphere. Okay, so if you set the north pole, a neighborhood of the sphere will be a circle, right? And inside the circle, but still on the sphere. Okay, so you can think about, okay, maybe I should bring like a basketball, right? So you can, but you know the basketball, right? So you're talking about, you look at the ball from the north pole, you look at the north pole. You will know what the meaning of the vicinity or a neighborhood of the north pole. Okay, and so a neighborhood of the north pole corresponding a neighborhood of the point at infinity in the extended complex plane. And as we have shown that, okay, this is just a neighborhood, right, of the north pole on the sphere. So that the corresponding point would be what? Would be the region, right, outside a big circle, okay, with radius r, outside a big circle. Okay, all right. So it makes sense to see that this one is a so-called R neighborhood. Okay, and if R become bigger and bigger, then the neighborhood of the point of unit becomes smaller and smaller, right? Just, okay, because as R bigger and bigger, the set becomes smaller and smaller. Okay, you can see that because we are taking that this is greater than R. Okay. Okay, so now. So with this kind of point of view, to investigate a complex function f of z for z with large magnitude, then we can set z to be 1 over w and investigate g of w. Okay, so define here. Okay, so z is 1 over w, right? In a neighborhood of w equal to 0. Okay. Because when z is big, then w becomes to be small, right? So when z goes to infinity, w goes to 0. Okay. And so to investigate the behavior of a function for z with large magnitude, then it's just the same as we investigate behavior of this new function of w in a neighborhood of w equal to 0. So, right? And so we can define some concept. So f of z is said to be analytic our singular at the point, okay, or at infinity. Okay, if g of w, which is defined to be 1 w, x analytic or singular respectively at w equal to 0. Okay. So now we are able to speak about the analyticity or singularity at the point of infinity. Okay. And so we also define that the value, okay, the value, okay, of a function, okay, at the point of infinity to be okay, and okay, to be the limit if it exists. Okay, if the limit exists. Okay, and so we say that f of z has an m's pole, m's order, 0 or m's order pole or isolated essential singularity or removable isolated singularity at infinity. Okay, if GW, which is f of 1 over W, has such a 0 pole isolated essential singularity or removable isolated singularity at the point w equals 0. Okay. Okay. All right. So let's take 5 minutes break up to 2:30. Okay, so let's take several examples. Right. So look at the this rational function. Right, and so as we see, when the magnitude of z goes to infinity, or when the magnitude of z is big, you can see the value becomes quite small. Okay, so to investigate the behavior of the function at the infinity, right? So we consider. So this becomes to be the square of w. So this implies that f of z is analytic at infinity. Okay, right. So it's analytic, and has a zero of second order. Okay, because here is w square at infinity. Okay, because this one, so that this one is analytic at w equals 0, and has a 0 of second order at w equals 0. Okay. See. All right. So as the magnitude of z becomes big, you can see the value of the function becomes big too. Okay. So you can, from here, you know, we must have singularity, right? At the infinity. Okay. All right. So we see GW. So this has become 2 here. Okay. All right, so this function is singular. So this one has an isolated singular point, singularity at w equals 0. Okay. And has a pole of third order. Okay, from here. At over 0. So this implies that fz, right, is a singular at infinity, and has a pole of third order. Okay, at infinity. The exponential function. Okay, so now we see now we have this, and this function has an isolated essential singularity at w equals 0, as we know before. Okay, so this W function, as I said, essential singularity. Okay, so this implies that f of z is isolated essential singularity at infinity. Now consider the function z and sine over z here. Okay. Now this means that we have sine down here. And this function, as we know, has a removable isolated singularity at w equals 0. So which means that f of z has a removable isolated singularity at infinity. Okay. Okay, so these four case examples covered the four cases we consider here. Okay. Zero pole, isolated essential singularity, removable isolated singularity there. Okay. I took a fifth example in my lecture notes, so I ask you to read it. Okay. Okay, and now the last subject in the second section of chapter 16 is about the meromorphic function. Okay, so meromorphic function is an extension of analytic function. Right. So now, as I defined it, a complex function f of z is said to be meromorphic in an open set omega in the complex plane. Right. If there exists a subset A of omega, okay, such that 1, A has no limit point in the open set omega. But A may have limit points outside omega, okay? We just require A has no limit point in omega, right? And the set, we know the set A is a subset of the open set omega here, okay? But we do not allow this subset A has any limit point, okay, in omega. But A can have, again, N can have a limit point outside omega, right, which is allowed. Okay. Second, F, right, is holomorphic in A remove in omega, but remove A there. Okay, see here. Third, Fz, okay, has a pole, all right, of finite order. At each point of A. Okay, so because of that reason, A is called the pose of the meromorphic function. F. Okay. All right. So a meromorphic function, okay, in an open set omega is almost an analytic function on omega, almost, except a subset A of omega. Okay. Okay. So the second point says that F is analytic, right? In this set omega, but set minus A. Okay. And the function F is singular, right, at every point of A. But that singularity should be isolated, okay? And each of the singularity is a pole of finite order, okay? So you can't have isolated essential singularity, all right? At any point of the A, you can't have, right? So every point of A is just a pole of finite order, okay, of the complex function of Z. And the most important thing is the first point. The set A has no limit points in omega. Okay, so that is very important. So if you have such a complex function, then it's called a meromorphic function in an open set omega. Okay. So with the concept of meromorphic function, we can discuss analytic function together with poles, together with the pole set of the function. Okay. So we can discuss them together, and that is important in application of complex analysis. So let me make several remarks, okay, about meromorphic function. All right, so if A is the empty set, all right, so if there's no pole set in omega, then of course F, right, it's a holomorphic function defined, okay, on the open set omega there. Okay, so this is so you can think about analytic function is a special kind of monomorphic function. Okay. Second, the set omega, set minus A, let's say is necessarily open, okay, in the complex plane. All right, so this is because that all right, if Z is a point in omega set minus A, then Z is not a limit point of A. So it's not a limit point. Because A has no limit point in omega. Okay? So any point outside in omega but outside of A, okay, is not a limit point of A. And by definition, so that the point Z has a neighborhood. All right? So it has a neighborhood in omega, okay, disjoint from A. Okay. I.e., the neighborhood will be contained in omega, but same as A. Okay. Right? So, because if every neighborhood of Z, right, not disjoint from A, which means that every point of Z contains a point in A, then Z should be a limit point by definition. Okay, so this is not true. So we find a neighborhood of Z, and the whole neighborhood is contained in omega, but same minus A. Okay. Okay. So every point in the omega same minus A, we can find a neighborhood contained in omega minus same minus A. Then this is just fulfill the definition of openness of this set. Okay. So again, this set is also an open set. Okay. Because as usual, we define an analytic function on an open set in the complex plane. Okay, so it will cause us no problem with that. Okay, so that is the point we have. The third thing is that A consists of isolated points, i.e., for each point Z in A, okay, there is a neighborhood of Z which contains, okay, no points of A different from Z. Otherwise, Z is a limit point of A, which is a contradiction. Okay, so that A consists of isolated points. The fourth comment is that A is countable. Okay, K is countable. So either A is a finite set, so the pole set is finite, or if it's infinite, then it's countable. Okay. All right. So please see. Right. So I give a reason why A is countable, and it becomes because it's involved the topology of the complex plane, so that I leave the detail for you to read. And the first point, it is possible that A, okay, has a limit point, okay, outside the omega. Let us take an example. Consider Fz, okay, which is 1 divided by the sine of 1 over 1 minus Z. Right, so this one, okay, so this function, so this function is meromorphic in the open set D, the open disk, and with the pole set at Z equal to 1 minus 1 over n pi. Okay, for n Yep. So we will so let's see why this is. Okay. So we okay. Now if z is 1, so that this is 1, and so we right. So we have the open unit disk here. So this is 0. And it has a pole when, okay, so Fz has so F is singular at Z if and only if we can see that the sign 1 over minus 2 is 0. Okay, and so which means that 1 over Z is m pi. Okay, for O and Z. Okay, and so which means that Z is equal to 1 minus, okay, okay, m pi for okay. Right, so did they have a single point? If this 1 minus pi. Okay, so now, so F now, so F of Z has a simple pole at Z equal to 1 minus 1 over m pi for all n which is equal to 1, but without 0. Okay. Okay, so this means that so it's never 0. Okay, so without 0. And but if n is negative, then this poles will be outside of the unit open disk. So you can like maybe you can have here, this is the n minus pi, etc. And you will have more. Okay. And similarly, you have the pole here. Etc. So this is in 1, 2, 3, etc. Okay. In the omega, which is okay. So the omega we consider is the open unit disk here. Okay. And then these poles will be simple poles. Okay. All right. So A would be 1 minus 1 over n pi, and n is from 1 to infinity. And this one is contained in the omega, which is d 1. All right, and first of all, A has no limit point. Okay, in omega. Okay, but A has a limit point at z equal to 1. Okay, so it has a limit point. Because you can see that as n goes bigger and bigger, it's approaching to 1. Okay, so this set has a limit point at z equal to 1. Okay, okay, so the A has a limit point outside, which is outside of omega. Second, the function is analytic in omega divided by z minus 8. Okay, so except at this point, the function is analytic. Okay, you can see. And third one, f of z has a pole at each point of A. Of course, the function has pole outside of the omega, of course, in this example. But because we just confine ourselves to the open disk D with this one is the open unit disk. So that Okay, so from that, so f equal to 1 over sine 1 over 1 minus z. Okay, so this function is meromorphic. Okay, so it's meromorphic in the omega, which is okay. So we say that it's meromorphic to that. Okay, and this is because we just restrict ourselves to the omega, which is just the open disk. If we consider the omega set to be the whole complex plane, then the pole set, you can see that you will have, so now you have a lot more pole set there, and the pole set has limit point. Okay, will have limit point there, and in that case, this function will not be meromorphic. Okay, so this is important. That we should know what open set we are going to consider, okay, as the in the definition of the meromorphic function. Okay, and from that open set we find the singularity, the set of singularity. Okay. And this set of singularity has no limit point in the selected open set. Okay. And the complex function f should be analytic in the open set, but minus the set of singularity. And every singularity, singular points in A should be a pole of finite order. Okay. So that you should justify that these three conditions are satisfied. Okay, in that case, then this function is called meromorphic in an open set omega. All right. So now I will state a theorem related to meromorphic function. Is about the reciprocal of analytic function on a domain. Okay, so let f of z be a non-zero analytic function on a domain. Remember, a domain is a special kind of open set, which is an open connected set. All right, and with zero set z. Right. Okay, so f is analytic function on a domain D, so that f has no singularity, okay, on domain D, and it has zero set, Okay? And the zero set we call Z. And of course that by theorem 16.2.b, that this zero set has no essential zero. Why? Because if in the zero set we have an essential zero, then this function should be identical to the zero function. Okay? Because it's an identity function on a domain D. Okay, so this function should, but we say fz is non-zero, so that, which means that the zero set contains no essential zero. Now, then the reciprocal one over f of z over f of z is a monomorphic function on D, and with pose equal to Z. Okay. So the operation of taking the reciprocal. Okay, so you take the reciprocal of analytic functions, then you will turn an analytic function to a meromorphic function. Okay, so it's not too bad in terms of, this means that it's not too bad. But at the same time, you will turn the zero set of the analytic function to the pose, to a pose, okay, of the meromorphic function. Okay. So that this is a nice theorem, because that people usually consider reciprocal of an analytic function, and we will know that. Okay. And the important thing is that the pose, okay, the zero set becomes to pose set, okay, become the pose set. All right, so let's see a proof for that. All right, so neither f of z has neither would have an essential zero in the domain D, nor the zero set Z has a limit point in D. Okay, so this is from theorem 16.2.b, and the zero set has no limit point. This is from theorem 16.2.c. Okay, remember. The analytic function is defined in a domain. Okay. And we know theorem 16.2.b and theorem 16.2.c only valid for analytic function defined on a domain. Okay, so it's very important to know that. Okay, so we have that. So the set Z has no limit point. Okay, so the first condition has been satisfied. A has no limit point. Okay, in D. All right. So thus Z the zero set consists of zeros of finite order. Okay, of F. Right, and by theorem 16.2.4, okay, Z is the pole set of the reciprocal. One over F of Z of F of Z. Okay, because in that theorem 16.2.4, we will turn a zero of m's order to a pole of m's order. Okay, we turn that. Okay. Right? So the zero set we come to the pole set. Okay, and so the third one, okay, and the third satisfied, and we know the F is also analytic at every point. Okay, so the reciprocal also is clear. So it is clear that F of Z is analytic in D minus Z. Okay. Right? Because for every point Z in D minus Z, F of Z is non-zero. Okay, so 1 over F of Z is well defined. Okay, so that is clear. This is analytic. All right, and so that this is the second condition, right? We have Z has no limit point, so this is the first condition we have. This is the sub condition we have. So by definition, F of 1 over F of Z is meromorphic. Okay, it's meromorphic in D. Okay. Okay. So meromorphic function can be obtained by doing the reciprocal of a non-constant, a non-zero analytic function. Okay, non-zero analytic function on a domain D. Okay. Okay. Any questions? All right. So I will do some additional lectures. All right. Tonight, and so you can. I think you will be able to watch the recorded class lecture tomorrow. Okay. So in the additional online lecture, I will cover the last two sections of this chapter. Yeah. Okay, so any questions about the material I covered today? Okay. All right, so if no, then remember that next Thursday will be our final examination. And the coverage of the final examination will be the material taught in this whole semester. Okay, so including chapter 11, 12, 13, 14, 15, and 16. Okay, so everything you will have. Okay, and so I will send you a notice to you again. Okay, so good luck with the final examination. Yes? No, just we'll have online lecture only. Okay, so no class lecture.